Hello guys and welcome back to my channel. And you know what's the time? What is the time? It's science time. Okay, so today let us discuss the quantum mechanics of black holes. Let's go. The first 30 years of this century saw the emergence of three theories that radically altered man's view of physics and of reality itself. Physicists are still trying to explore theories that are special theory of relativity slash 1905, the general theory of relativity slash 1915, and the theory of quantum mechanics slash 1926. Albert Einstein was largely responsible for the first and was entirely responsible for the second and played a major role in the development of the third. Yet, Einstein never accepted quantum mechanics because of its element of chance and uncertainty. His feelings were summed up in his oft-quoted statement, God does not play dice. Most physicists, however, readily accepted both special theory of relativity and quantum mechanics because they described effects that could be directly observed. General relativity, on the other hand, was largely ignored because it seemed too complicated mathematically. It was not testable in the laboratory and was a purely classical theory that did not seem compatible with quantum mechanics. Thus, general theory of relativity remained in the doldrums for nearly 50 years. The great extension of astronomical observations that began in the early 1960s brought a revival of the interest in the classical theory of general relativity because it seemed that many of the new phenomena that were being discovered, such as quasars, pulsars, and compact X-ray sources, indicated the existence of very strong gravitational fields that could be described only by general relativity. Quasars are star-like objects that must be many times brighter in entire galaxies, as if they are as distant as the reddening of their spectra indicates. Pulsars are rapidly blinking remnants of supernova explosions, believed to be ultra-dense neutron stars. Compact X-ray sources revealed by instruments aboard space vehicles may also be neutron stars or may be hypothetical objects of still higher density, namely black holes. One of the problems facing physicists who sought to apply general relativity to these newly discovered or hypothetical objects was to make it compatible with quantum mechanics. Within the past few years, there have been a few developments that give rise to the hope that before too long we shall fully have a fully consistent quantum mechanics theory. The one that will agree with general relativity for macroscopic infinities that have long bedwelled other quantum field theories. These developments have to do with certain recently discovered quantum effects associated with black holes, which provide a remarkable connection between black holes and the laws of thermodynamics. Let me describe how briefly a black hole might be created. Imagine a star with a mass 10 times of that of the sun. During most of its lifetime of about a billion years, the star will generate heat at the center by converting hydrogen into helium. The energy released will create sufficient pressure to support the star against its own gravity, giving rise to an object with a radius about 5 times of the sun. The escape velocity from the surface of the star would be about 1000 kilometers per second. That is to say, an object fired vertically upwards from the surface of the star with a velocity of less than 1000 kilometers per second would be dragged back by the gravitational field of the star and would return to the surface, whereas an object with a velocity greater than that would escape to infinity. When the star has exhausted its own nuclear fuel, there would be nothing to maintain the outward pressure. The star would begin to collapse because of its own gravity. As the star shrank, the gravitational field at the surface would become stronger and the escape velocity would increase. By the time the radius had got down to 30 kilometers, the escape velocity would have been increased to 300,000 kilometers per second, the velocity of light. After that time, any light emitted from the star would not be able to escape to infinity, but would be dragged back by the gravitational field. According to the special theory of relativity, nothing can travel faster than light. So, if that light cannot escape, nothing can either. The result would be a black hole, a region of space time from which it is not possible to escape to infinity. The boundary of the black hole is called the event horizon. It corresponds to a wave front of light from the star that just fails to escape to infinity but remains hovering at the squashy radius, which is 2 equals to gmc, where g is Newton's constant of gravity, m is the mass of the star, and c is the velocity of light. For a star about 10 solar masses, the Schwarzschild radius would be about 30 kilometers. There is now fairly good observational evidence to suggest that black holes of about this size exist in double star systems such as X-ray source, also known as Sinus X1. There might also be quite a number of very much smaller black holes scattered around the universe, formed not by collapse of the stars but by the collapse of highly compressed regions in the hot, dense medium that is believed to have existed shortly after the Big Bang in which the universe originated. Such primordial black holes are of greatest interest for quantum mechanics. I shall describe here a black hole weighing about a billion tons, about the mass of a mountain, would have the radius about 10-13 centimeters, the size of a neutron or proton. It could be in orbit around the sun or around the center of the galaxy. The first hint that there might be a connection between black holes and theorodynamics came with the mathematical discovery in 1970 that the surface area of the event horizon, the boundary of the black hole, has a property that is always increased when additional matter or radiation falls into the black hole. Moreover, if two black holes fall and collide and merge into one single black hole, the area of the event horizon around would be resulting in the black hole much greater than before. These properties suggest that there is a resonance between the area and the event horizon of black hole and the concept of entropy in theorodynamics. Entropy can be regarded as a measure of the disorder of a system, equivalently as a lack of knowledge of its precise state. The famous second law of thermodynamics says entropy always increases with time. So that's it what I know about for right now. It's your boy Divi who will bring more research on the quantum mechanics of black holes. It's your boy Divi. Stay tuned. Bye bye. Wait a second. Am I forgetting something? Oh yeah. Fact of the day. Fact of the day. Did you know that When you are born, 60,000 of your cells are already dead and replaced by new ones. It's your boy Divi. Bye bye, stay tuned, and see you tomorrow. Don't forget to like, subscribe. Bye.